Somewhere in the darkness of the constellation Fornax, sitting behind a patch of sky so unremarkable that no telescope had ever bothered to stare at it for long, there is a smudge of light so faint it should not have been detectable by any instrument humans have ever built. And yet, in the data that came back, that smudge was not faint because it was small or dim in any ordinary sense. It was faint because of something far stranger. That light left its source before most of the universe, as we understand it, had even finished forming. By the time it reached the mirrors of the James Webb Space Telescope, it had been traveling for over 13 billion years. And when scientists finally confirmed exactly how far away it was, exactly how early in cosmic history it existed, more than one astronomer described the discovery using a word you almost never hear in a peer-reviewed paper: impossible. This is not an exaggeration for the sake of drama. This is the actual language some of the leading researchers in observational cosmology have used to describe what James Webb has been finding since it started its science operations. Not because the galaxies themselves are unbelievable objects floating in space doing something physically impossible, but because their sheer existence, this early, this massive, this structured, does not fit comfortably inside the models that cosmologists spent decades building and refining. And now those models are being pulled apart and rebuilt in real time in public, while the rest of us watch. To understand why a single distant smudge of light can shake an entire field of science, you first have to understand what looking far away in space actually means. Light does not move instantly. It travels at a fixed, finite speed. And no matter how advanced your telescope is, you cannot outrun that limit. Every single photon of light that reaches your eyes right now, in this exact moment, left its source in the past. Look at the sun, and you're seeing it as it was about 8 minutes ago. Look at a star 100 light years away, and you're seeing light that left before your grandparents were born. This means telescopes are not just tools for seeing things that are far away in space. They are literal machines for seeing backward in time. And the further out into the universe you can detect light, the further back into cosmic history you're actually looking. This is the entire reason James Webb was built the way it was. At a cost of roughly $10 billion and more than 2 decades of engineering, launched on Christmas Day in 2021, after generations of delays and redesigns. Its predecessor, the Hubble Space Telescope, had already pushed the boundary of how far back we could see, capturing galaxies that existed when the universe was just a few 100 million years old. But Hubble was built primarily to observe visible and ultraviolet light, and there is a fundamental problem with looking that deep into the past using visible light alone. As the universe expands, the wavelength of light traveling across it stretches along with it, a phenomenon called redshift. Light that started out as ordinary visible light, emitted by young, blazing stars in the early universe, gets stretched by billions of years of cosmic expansion until, by the time it reaches us, it has shifted entirely out of the visible spectrum and into infrared. Hubble, in many cases, simply could not see it anymore. It wasn't that the light wasn't there. It was that Hubble's instruments were the wrong tool for catching it. James Webb was purpose-built to solve exactly that problem. Its giant 18-segment gold-coated mirror, spanning 6.5 meters, and its suite of infrared instruments were designed specifically to catch this stretched, redshifted light from the earliest galaxies in the universe, light that had been traveling toward us since almost the very beginning of everything. One of the earliest and most striking discoveries came through a research collaboration known as JADES, the JWST Advanced Deep Extragalactic Survey, a project designed specifically to stare deeply and patiently into small patches of sky and catalog everything faint and distant hiding within them. Among the galaxies this survey uncovered was one that would eventually be named JADES GS30, a designation that tells you almost everything about why it mattered in that single number tucked into its name. The Z refers to redshift, and a redshift of 13 meant this galaxy's light had been stretched by an almost unbelievable amount on its journey to us, placing its existence at just a few 100 million years after the Big Bang itself. Then, in 2024, an even more extreme discovery followed. A galaxy designated JADES GS Z14-0, confirmed through detailed spectroscopic analysis, was found to have a redshift of just over 14, corresponding to a time when the universe was only around 290 million years old. To put that into some kind of perspective, if the entire current age of the universe were compressed into a single calendar year, that galaxy would be forming in the first few days of January. And yet, this was not some faint, formless smudge of gas struggling to become something. Analysis of its light showed a surprisingly bright, structured galaxy, actively forming stars at a rate that genuinely startled the researchers who studied it. That word, bright, is where the real scientific tension begins. Cosmological models built up over decades, largely based on our understanding of how gravity slowly pulls gas together after the Big Bang, predicted that galaxies this early in the universe's history should be small, faint, chaotic clumps of star formation. barely galaxies at all in any organized sense. Structure takes time to build under gravity. Stars need to form, live, and sometimes die before enough heavy elements exist to fuel more complex star formation. Galaxies need mergers and gravitational interactions across hundreds of millions of years to grow into anything resembling the organized massive systems we associate with galaxies today. The math, built on the standard model of cosmology that has successfully explained an enormous range of observations for decades, simply did not predict galaxies this bright, this massive, and in some cases this structured, existing this early. And yet James Webb kept finding them. Not just one anomaly, but a whole population of galaxies significantly more luminous, and by extension, apparently more massive, than the standard models expected for their age. Some early estimates of these ancient galaxies' stellar masses, based on relationships that hold up remarkably well for closer, better understood galaxies, produced numbers so large that a few researchers describe them as almost too massive to exist, given how little time had passed since the Big Bang for stars to have formed at all. Astronomers began informally referring to some of these objects as universe breakers, not because anyone genuinely believed the universe was broken, but because these galaxies broke the confident predictions astronomers had built their careers on. This is the part where good scientists do exactly what good scientists are supposed to do. They question their own assumptions before questioning the fundamental laws of physics. And in this case, several of those assumptions turned out to deserve real scrutiny. One leading possibility is that black holes at the centers of some of these early galaxies are growing and feeding far faster than expected. And the light from material being violently heated as it spirals into these black holes can mimic and inflate the apparent brightness that astronomers were interpreting purely as starlight. If some portion of that dazzling early light is coming from active supermassive black holes rather than star formation alone, it would mean these galaxies are not quite as impossibly massive in stars as the first calculation suggested, even if the black holes themselves raise an entirely separate and equally strange question about how something that large could form so quickly. Another possibility researchers have taken seriously involves star formation efficiency in the early universe. The models used to estimate galaxy mass rely on assumptions about how efficiently gas converts into stars, assumptions calibrated against galaxies much closer to us in time and space. If the early universe, with its different chemical composition and different physical conditions, allowed gas to collapse into stars with far greater efficiency than we see happening in the modern universe, that alone could explain some of these galaxies appearing far brighter and more massive than expected, without requiring any dramatic revision of cosmology's fundamental structure. But even accounting for these more conservative explanations, something genuinely unresolved remains. The sheer number of bright, seemingly evolved galaxies James Webb has found at these extreme redshifts is higher than most pre-launch predictions anticipated, and multiple independent research teams using different methods and different data sets have converged on similar conclusions. This is not a single quirky data point that will quietly disappear with more careful analysis. It is a pattern, showing up again and again as James Webb continues its survey work, and patterns are exactly what force scientific fields to seriously reconsider their foundational assumptions, rather than simply patching around a single inconvenient result. What makes this entire situation remarkable rather than alarming, at least to the scientists actually doing the work, is that this is precisely how major scientific progress has always happened. The standard model of cosmology, often called lambda CDM, remains one of the most successful scientific frameworks ever built, correctly predicting an enormous range of observations about the structure, composition, and evolution of the universe, from the leftover glow of the Big Bang itself to the large-scale distribution of galaxies across billions of light years. Nobody studying these early James Webb galaxies is seriously proposing to discard that framework. What they are doing is exactly what the framework demands when new data does not fit smoothly, refining it, testing its edges, and figuring out exactly which specific assumptions about early star formation, early black hole growth, and early galaxy assembly need adjustment. There is something almost poetic about the fact that a telescope purpose-built to look further back in time than any instrument before it immediately found evidence that our understanding of that exact period was incomplete. James Webb was never going to simply confirm everything scientists already believed and move on quietly. Telescopes built to push into genuinely unexplored territory tend to find genuinely unexpected things, and that is not a failure of the mission. It is, in a very real sense, the entire point of building it in the first place. Consider what these galaxies actually represent physically. Light that left its source when the universe was less than 2% of its current age, traveling in a straight, uninterrupted line for over 13 billion years, through the expansion of space itself, through the formation and death of countless stars, through the assembly of galaxies, including our own, arriving finally at a golden mirror built by human hands and launched 1 million miles from Earth to a stable point in space called the second Lagrange point, specifically chosen, so the telescope's own heat and light would not interfere with the impossibly faint signals it was built to detect. That mirror gathered photons that are, quite literally, older than almost everything else you have ever seen or touched in your entire life, and turned them into data that human beings then used to reconstruct the shape, brightness, and composition of a galaxy that formed before our own Milky Way even began assembling itself. And this is very likely not close to the limit. Each new James Webb survey pushes the boundary of what has been confirmed a little further, and multiple candidate galaxies with even more extreme redshifts, suggesting even earlier formation times, are currently working their way through the careful spectroscopic confirmation process that separates a solid, peer-reviewed discovery from a tentative, unconfirmed signal in noisy data. Scientists are deliberately cautious here because claiming a new record for the most distant galaxy ever observed carries real scientific weight, and premature claims that later get walked back can damage trust in the broader body of research. So confirmed distances tend to lag behind candidate detections by months or sometimes years, as teams cross-check results using different instruments and different analysis techniques before publishing anything with full confidence. What this all points toward is a genuinely open and active area of cosmology, unfolding in something close to real time. Unlike many corners of physics, where the fundamental questions were settled generations ago and only fine details remain to be worked out, the question of exactly how the first galaxies in the universe formed, how quickly they grew, and how massive they were able to become within just a few 100 million years of the Big Bang is a question actively being rewritten as new data arrives. Textbooks published even a handful of years ago already describe an early universe less dynamic and less structured than what James Webb is now revealing it to have actually been. There's also something worth sitting with beyond the pure science, something closer to perspective. These discoveries are not really about distant smudges of infrared light or contested stellar mass calculations. They're about the fact that human beings, standing on a small rocky planet orbiting an unremarkable star, built a machine capable of catching light older than nearly everything else observable in existence, and used it to look back far enough to see the universe still in its infancy, still assembling the very first generations of galaxies, one of which would, unimaginably far in the future, eventually give rise to a planet, a species, and eventually a telescope capable of looking back at where it all began. The universe, it turns out, was busier, brighter, and more surprising in its earliest moments than anyone confidently predicted before James Webb switched on. And every new image, every new confirmed redshift, every new galaxy that shouldn't quite fit the models but does exist anyway, is a small reminder that the story of how everything came to be is still being written, refined, and in some cases completely rewritten, based on light that has been traveling toward us since before almost anything else in the universe existed at all.